Okay, I think we're ready to start. Welcome everybody, and welcome to Erik Schnetter, who is gonna introduce us to his MPItrampoline library, which is a lightweight library that forwards MPI calls to other actual MPI implementations. The floor is yours, Erik.
Thank you. Thanks for having me today. It's a pleasure to be here. I'm talking to you from Waterloo, Ontario, Canada, since we can't see each other in the real world. And today is a beautiful, crisp, sunny winter day outside here. If you're living in the Northern Hemisphere and hoping for snow and don't have it, then I should send you a picture. During my presentation, I'd be happy to answer questions at any time. I hear there's a Slack channel, or you can talk in the Zoom chat. I might not see it, but one of the hosts will interrupt me. And I love interactive presentations. Since I don't know the audience here, but I assume you're somewhat technical, I broke the talk into two pieces. In the first half, I'm going to discuss why MPItrampoline is a really good idea and how it looks from the user's point of view. And in the second half, we get a bit more technical and talk about some of the implementation issues. So since this is about MPI, and although I assume that most of you know what MPI is, I want to clarify a few details. MPI is a standard for distributed computing. It's a source level standard that is essentially targets the C programming language. And what it basically allows you to do is to send and receive messages between processes that are probably running on different nodes of an HPC system. It's a standard that came about in the early 90s. There's a webpage, mpiforum.org, and the standard is very successful. There are many MPI implementations. The two foremost are MPItch and OpenMPI. Both are open source. And then all the big vendors have their own MPI implementations, Cray, IBM, Intel, Microsoft, and probably many more. And I have the feeling that they're basically all put their MPI implementations on top of either MPItch or MPI. It's possible because these are available as open source. And if you use MPI, that looks as follows. You have your program and you run many copies of the program simultaneously on different nodes of an HPC system, essentially different workstations. And you can either send and receive messages between two individual nodes. There are collective operations, barriers, broadcasts, reductions, sum or maximum or similar. You can even allow other processes to read from or write to your own memory. It's kind of distributed shared memory. There's parallel IO and so on and so forth. There's a host of things that MPI offers. The programming model is also called CSP, communicating sequential processes. Each of the processes is a regular process. There's nothing parallel going on and they communicate. And that programming model is very 1990s. It's somewhat object-oriented, right? Message passing and so on. But there's a lot of global state involved. So that programming model is a bit dated. Many people hate it. I'm not a big fan of it either. But MPI is portable. It supports many communication mechanisms. And it's ubiquitous in HPC computing and high-performance computing. Essentially, if you say you're doing high performance computing and you're not using MPI or you don't know about MPI, then you're probably sitting in a very small corner of high performance computing. I'm not saying MPI is good. I try to give a neutral overview here. And when we talk about high performance computing, then of course it's about performance, and performance always has two sides. And one side is about bandwidth or throughput. It's measured in bytes per second or interactions per second. For example, you might want to process a terabyte of data, and each of your nodes can handle 10 gigabytes per second. And then you can probably scale it up quite easily. If you're using more nodes, 10 times as many nodes gives you 10 times the bandwidth. So bandwidth is usually straightforward to scale. And this is where cloud computing sits. If you don't know how big your problem is ahead of time, or if you suddenly realize you need to solve a problem that's 100 times larger than expected, and you have the money, then cloud computing could help you here. But the other side of performance is latency, and there's the minimum wait time to get one thing done. And if you talk about communication, that's also called the ping time. It's the time that it takes for one node to send one message to another node and for that other node to reply and send a message back. And while bandwidth scales easily, latency doesn't. If at all, if you use more nodes, then you have a more complicated networks, more layers of switches and routers in between, and your latency will go up. So if your problem is dominated by latency, then scaling doesn't really help. Then you need to do something else. And here's an example. If you have a modern Ethernet, 10 gigabit Ethernet, using TCP via Unix sockets and so on, then the latency, the ping time, is between 10 and 100 microseconds. A usual ping time that you see on Unix is, say, a millisecond or a tenth of a millisecond, and 0.1 millisecond is 100 microseconds here. And if you use an HPC network, special interfaces, special cables, and so on, using InfiniBand or some of the other network providers, then the latency can be 10 times lower. That means it's 10 times faster, between 1 and 10 microseconds. And it's really difficult to get smaller because there are weird things happening with how long it takes for one CPU to switch context between two threads and so on. That can already take several hundred nanoseconds. And the advantage of MPI is that they're not just allowing you to get the high bandwidth, of course they do that, but one of the big points about MPI is that they give you, in a portable manner, access to high performance network interfaces, the special purpose hardware that reduces the latency by an order of magnitude, corresponding to a very expensive off-the-shelf product. And this is one of the reasons why people like MPI, the portability and access to these high performance network interfaces. And let's now switch tracks a bit. How does one install software? If you grew up in the 90s on Unix environments, then the philosophy, and that is outdated today, is that you want to build from source. In the 90s on Unix, that was the only portable thing, because in the 1990s, there were probably 10 different CPU architectures, 10 different Unix operating systems that existed, and binary compatibility was impossible to achieve because there was a huge market of different hardwares and architectures and operating systems. But things have changed. These days, packages are more complicated, they have more dependencies. And actually, this is an EasyBuild Tech Talk, so you all know about that. Building from source is slow. It's fragile because you need the right tools installed, and the small deviations from a recipe could break anything. It requires substantial expertise to do that. Most regular HPC users cannot install a large dependency tree of softwares, and also the result is basically not reproducible. And of course, the good thing these days, what people do is you download binaries with pre-built software. That's how Red Hat on Ubuntu works. Nix works that way. If you need external dependencies in Python, you use Anaconda. In Julia, you use Yggdrasil. And of course, in commercial software development, there are Docker images. Before Docker, there were virtual machine images. And before people had virtual machines, they distributed disk images. And this is actually the first time I heard about that. When CERN wanted to do data analysis, probably 15 or 20 years ago, they wanted it reproducible. So they shipped the disk image, and then people installed that disk image on their HPC nodes. And then they needed to boot that node from that disk image, and then you have a reproducible environment. And everything since then, the moving from disk images to Docker images, is, from my point of view, that no new capability has been added. It's just making it easier, they're making it faster, more comfortable. But reproducibility was essentially solved that time. And we had discussions 15 years ago with people from CERN who wanted to use MPI. They didn't just want to have these naturally parallel processing algorithms where you run one process on one node and another process on another node. They wanted to communicate. They had heard that MPI is a good way of doing that, and they tried to incorporate MPI into their disk images, and they couldn't. Something was wrong there, and they didn't quite understand why MPI wasn't working, and I didn't either. But this year, we found out why. And there's something special about MPI, and that makes it break all these things. And that is quite sad, actually. And Here's the reason. MPI is a source level standard because it was devised in the early 90s and everything was source level at then. And MPI libraries cannot be installed as a binary. If you have a precompiled MPI library or want to use it on an HPC system, say a Cray system, that wouldn't work because MPI libraries access system hardware, these high performance network interfaces that I mentioned earlier. They either need to access the hardware or kernel drivers or need to be linked against particular versions, maybe especially patched versions of low-level system libraries, or maybe they need to configure to access a particular hardware as if they were a device driver. That's essentially what MPI is. And that means you need to build or install MPI on the node. And since MPI is a source level standard, that means all software that uses MPI must be installed from source everywhere where you want to run it. And that means decades of advances in package management is down the drain right here. And that also means that EasyBuild and Spec and so on, they cannot realistically offer binary packages for HPC systems because each HPC system is special. They have different MPI libraries. And that is the big problem. That's why I put it in red here. If you want to do high performance computing, you have a very high incidental complexity. There's nothing a priori that's too difficult about that, but not being able to install binaries for a software means that everything becomes difficult and slow. And luckily, EasyBuild and Spec are around and make it easier to do things, but things could be much easier. So this is the problem statement. And now I'm going to suggest a particular solution. And one solution is that you have an MPI ABI, a binary interface. What if MPI implementations were binary compatible so that at runtime you could switch out one MPI implementation for another? And the approach is essentially the system-specific bits of MPI should be installed by a system administrator, and the application links to a generic MPI interface. When you build the application somewhere on a CI system, and you download the binary on an HPC system, and they talk to each other via this API, and everything is much easier. And this way of working is well known. For example, that's how libc on the operating system kernel, say the Linux kernel, how they talk to each other. If you have to install a new Linux kernel, you don't need to recompile all the software on your system, but rather libc uses a binary API to talk to the kernel. That works fine. And this is also the case for CUDA and CUDA drivers. When you download CUDA, you might think there's one thing, the big CUDA package, the 10 gigabytes that you're getting, but actually it comes in 2 bits. One is CUDA and the other is the CUDA driver. And on an HPC system, the CUDA driver would be installed by a system administrator, and you can bring your own CUDA. So I was working on Perlmutter, an HPC system from the Department of Energy 2 weeks ago. And they had only CUDA 11.4 installed on the system, and something wasn't working. So the official advice from the system administrators was, well, just download and use 11.5 yourself. So you can just download your own version on CUDA, and it works because the hardware-specific bits, the CUDA driver, is already there, and they're presumably using some kind of API, and you can have version mismatches there, and everything is fine. And that's what we need for MPI. We need something that decouples the application from the details of the MPI application. And of course,
Erik, we have a comment or / question from Maxime from Compute Canada. He's asking regarding your claims on having to build MPI from source. So he's saying, what about OpenMPI's dynamic plugin loading? It's easy enough to build OpenMPI from source that loads what is needed from the system at runtime.
Yes.
And then, yeah, he's just continuing. He says on the Compute Canada clusters, we have a single OpenMPI build that works just fine on Ethernet, Omnipod, and InfiniBand. And at worst, you just have to set a couple of environment variables.
Very good. Yes, this is something I forgot to put in my talk. So thank you for the comment. So OpenMPI is one of the big open source implementations, and they put a lot of effort on binary compatibility. And that means if you build your application against one major version of OpenMPI, that's version 4 currently, then you can essentially at runtime talk to other OpenMPI implementations if they use also version 4. And that is fine, except that only works on HPC systems that use OpenMPI or a closely related MPI system. It would not work on a Cray system, which is based on MPItch. I'm sure they do their own thing within MPItch, but then there is still the problem of a mismatch there. And then, of course, there are other systems. And later on, I'm going to describe the problem that I actually want to address, which is for the Julia package manager. And we really want to have a single thing. So if the world could decide to use OpenMPI, or if MPItch could be made binary compatible with OpenMPI, then the problem would be solved and I would be happy and we didn't need MPItrampoline. But there are different MPI implementations and that you can switch between OpenMPI and I don't know, probably Spectrum MPI as well. That is quite nice, but that only solves about half of the problem. But the approach that OpenMPI uses is very much the same that I am using with MPItrampoline here as well. Okay. Do you want to make another comment, Maxime?
I don't see him posting additional comments, so maybe you can continue.
Very good.
And,
yeah, no, thank you for that comment. I like getting feedback, particular critical of my work. That keeps me on my toes. So I'm sorry, let me gather my thoughts. Yes, the basic idea is that we want to have a generic mechanism, an ABI for MPI that works everywhere. And the idea is also that it should work today. I don't want to design a standard that's available 5 years down the road. I want to have something that's maybe a bit more kludgy, but that can be used today immediately to solve the problem. And this is the basic outline of how MPItrampoline works. So here you have your application, and your application links against MPItrampoline, not against any system MPI. And MPItrampoline looks like a real MPI library, except it's a hollow shell, doesn't have any of the actual capability in there. And the application and MPItrampoline, it all happens on the user side. You can essentially wrap it up as a binary and ship it as a binary to an HPC system. And on the HPC system, you have the actual MPI library, or probably 2 or 3, where you would wrap it in an MPI wrapper. It's kind of the counterpart of MPItrampoline. And then at runtime, when you run your MPI, when you run your application, you use an environment variable, same what Maxime said before, to point it to a particular MPI wrapper that is then loaded at runtime, and that is then the MPI implementation that is used. So it is, I assume, the very same mechanism, very similar to the mechanism that OpenMPI uses, except it's more generic. It works for all MPI implementations. So MPItrampoline looks like a real MPI implementation, except all the MPI calls are forwarded after it loads an MPI wrapper. And MPI wrapper provides a translation layer. That's the one that OpenMPI wouldn't, because in the actual MPI library, they made certain changes, and these changes are different for every MPI implementation. And the MPI wrapper translates it to a well-defined ABI that is then used here to communicate. And then you could have different MPI wrappers on an HPC system, and you could point to a different one as well. And there's another project, not MPItrampoline. It's called the Wrapper Interface for MPI that is older than MPItrampoline. And there's a story why I developed MPItrampoline and didn't go with this project. But in hindsight, I don't know whether that was a good choice to do my own thing and not instead to contribute to the wrapper interface for MPI. These images are taken from their GitHub website, and the approach is very similar at the high level. At the lower level, they actually work differently. And they have 2 modes of operation. And one of the modes of operation, your executable links against the wrapper interface, and then at runtime to choose which MPI implementation to use, OpenMPI, Intel MPI. They also support MPItch and so on. Okay,
Just go ahead, glitch.
Okay, very good. You can then also choose which MPI implementation to use at runtime. I'm not an expert at the wrapper interface, but it seems to me that they do more translating at runtime. If there is an expert on the wrapper interface for MPI here in the audience, and you want to say something for 2 minutes, I'd be happy to wait. Otherwise, I'll just continue. It's just since this is a very similar project, I don't want to diss the project. And if you want to say something about it, here would be an opportunity. Now, if you use MPItrampoline, that just repeats the things from 2 slides ago, what you do, you build your application against MPItrampoline as the MPI library in the usual way, nothing special there, and you can ship that at the binary. On the target system, you need to build the MPI wrapper around every MPI library there. It's ideally done by a system administrator, and that needs to be only done once on every target system. It's kind of a startup. And then runtime, you then set an environment variable or similar to point to the MPI wrapper that you use, and then you're running with that MPI implementation. And MPItrampoline is, I'd say, ready for production use, but we don't have any big users yet. Call it beta quality, because there are probably bits and pieces that break as you scale out usage. And currently working on integrating MPItrampoline with the Julia MPI bindings, and that is actually the driver for this project. I didn't want to start MPItrampoline for itself, but I want to be able to use Julia and its package manager on HPC systems. And for that, I want to be able to download not just Julia, but also all its external dependencies that you might have. And that's the URL for MPItrampoline. And talking a bit about Julia, Julia has a package manager, its own package manager. And that package manager is very much built on distributing binaries to make it easy. If you say need HDF5 and on a regular laptop, people download HDF5 and build it, even if it works fine, that takes 20 minutes, and that is really inconvenient. I tried teaching a class where people use Julia. I taught them about HDF5. That was years ago before Julia had the good package manager. And half the time, people just waiting for this HDF5 binary to be built. And these days, of course, you said add HDF5. A minute later, it's all there. A binary provided for every platform. It's beautiful. I mean, we all know Red Hat and Ubuntu. It's the same thing. And when it comes to MPI, it's very important that within a whole application, that's both the Julia and all the other external libraries, FFTW, HDF5, Petsio, and so on, that they use exactly the same MPI library. Because the thing is that MPI is initialized at once, and then you get your communicator object, and you pass this communicator object to other places. So if you want to do a Fourier transform with FFTW, then the main program starts up MPI and passes the communicator to FFTW. The communicator essentially describes how processes talk to each other and how the data are laid out across the memory of the HPC nodes. You need to obviously use the same MPI implementation because that communicates an opaque object, points to some state that the MPI library maintains. That is, if you build FFTW against some binary MPItch, and then at runtime, the Julia MPI would use the system MPI, then that would not work. That would give seg faults. And because it's all about loading shared libraries, and there's no type system, no safety, everything on the surface looks fine, except you get seg faults. There's a really tedious way of debugging it. So there needs to be one MPI implementation. And since Yggdrasil wants to build all the packages ahead of time, you need to have an MPI implementation that doesn't know about the system MPI implementation. And if you want to use Julia on a Cray system, then you need to support MPItch and OpenMPI and all the others. So our goal for Julia is to use MPItrampoline for that. And to make it easy, we ship with an MPItch as fallback. So if you point MPItrampoline to a system MPI, that's the one that's going to be used. And if you don't do that, if you just run your laptop, it uses the built-in fallback. That was that about Julia. And next would be part 2 of the talk, where I talk a bit about how MPItrampoline looks under the hood. This would now be a good time to interrupt me, ask a few questions if you have some. And if not, I will continue. So now I'm going to talk a bit how the MPI ABI works. The MPI standard defines a few things. Some would be, say, compile times the constants. For example, max error string, the maximum length of an error string that MPI would produce, so you can allocate a buffer for that. And in our MPI ABI, we just define that large enough so that we can hold all the error strings. We don't have to cut them off. Alan, you have a question?
I just see in the YouTube stream that there's actually two questions or comments here. I think some implementations do provide binaries. For example, MVA pitch 2. I think they might be talking about the GPU stuff there, that they actually ship binaries of libraries. I remember they used to do that for the GPU supported stuff.
Okay. So it is possible, of course, to have a binary for MPI. If you think about Ubuntu, for example, you say apt-get install mpitch or apt-get install OpenMPI, you get a binary. But these binaries do not know about the very specific hardware that is available on an HPC system. They work well on a laptop, on a workstation. But if they should work with a particular InfiniBand or C-star library that an HPC system have, that would not work. And I actually tried to go down that route. I thought OpenMPI would be a good basis for the very same reason that Maxime mentioned earlier, the binary compatibility. And then I tried to have a binary MPI and install it on an HPC system and make it use all the nice network interfaces there. And I failed. I kind of spent half a year doing that, talking to various system administrators, but it doesn't work. You really need to build the MPI library on an HPC system against the very specific environment settings they have here. You can't use the binary.
And there was a second question then, which maybe I don't really understand. It says, why does there have to be a wrapper? Couldn't we use libffi to do it completely at runtime? I don't know libffi very well.
I don't know libffi either. And what one could do is MPItrampoline could call a particular function in the MPI library, got library version string, and then determine what MPI implementation it is, and then kind of using pre-encoded knowledge about what various types and internals it uses. But I didn't want to do that because then you only support particular MPI versions. MPI is a source level standard. So if you want to find out which of the functions are implemented via a hash define and which are actual functions and which are implemented via function pointers, then you need to compile some code here on the target system. I don't think there's any other reliable way than using a C compiler. And you might be able to run the C compiler at runtime. But running a C compiler at runtime is, again, difficult because you need to load the right modules and have the right version of the C compiler to do that. This is why I suggested that should be done ahead of time by a system administrator or an experienced user or someone who carefully reads the web pages of an HPC system. And then you have the MPI wrapper. Ideally, all the MPI implementations on the planet would come with an MPI wrapper, either for MPItrampoline or some other project that becomes more widely used, and then offer that ABI. Alan, I see you lowered your hand, but Maxime?
Yeah, that's all for me for the time being, at least from the YouTube.
Thank you.
Maxime?
Yeah, so I'm curious. You said you tried to do it with OpenMPI, but it didn't work. Well, what problem did you encounter? Because the Compute Canada software stack, we actually do that. We have a single build and it works on multiple hardware.
Yes. So what I wanted to do is have an MPI library that I build and then distribute as a binary. So on a Compute Canada system, I would download that pre-built MPI and then use it with not just the TCP Ethernet, but the actual high performance network there.
Right, that's what we do.
And that worked for you. Okay,
yeah.
Very good, very good. And I think I don't recall, it was either Graham on Compute Canada or it was Niagara. And I believe I talked to some administrators there, but this was probably 2 years ago. It was also in the context of me trying to use Docker images to run there, because just downloading binaries is inconvenient. Binaries in a Docker image would be nicer. And then you have your own MPI library inside the image when it runs inside the container, and it talks to something outside. And well, if that works now, that is good. And it was certainly not a big research project that I ran. It was something that I tried because I wanted to make it easier for other people to use. At that time, it was the Einstein toolkit. And yeah, after I realized that, of course, you can't use OpenMPI at all on a Cray system because there's system-specific libraries, and that is all based on MPItch there. I decided that shipping binaries was not a good idea. At that time, I then switched over to using spec. I'm sorry, that's an EasyBuild talk, but I have historic connections to the spec community here. Using spec on various systems to do things. And with spec and building from source on all HPC systems, I have something that's good enough for me, but it's still way too complicated. And my hope is that something like MPItrampoline is better.
And I think Bart has a comment as well.
Yeah, I can just add to Maxime in the sense that yes, on Compute Canada we have an OpenMPI that works on a variety of hardware.
I'm sorry, I cannot hear you.
Yeah, very low volume, Bart.
Let me get the gain.
He's trying to fix it, I think.
Okay, gain of microphone at 100%.
Yeah, that works.
Okay.
Thank you.
Yeah, no, what I wanted to say is that even though, as Maxime says, our OpenMPI works on a variety of hardware on a single binary, it depends on a bunch of other libraries, and you're basically just moving the problem to a lower level, and that is not solved. So our OpenMPI directly links to a particular version of UCX, to a particular version of libfabric. And a different system may have different versions of UCX, and they're not completely compatible with each other. I think there are some efforts in making those libraries ABI compatible across versions, but it's still kind of a moving target at the moment.
Yes, thank you. So the advantage of putting that thing at a lower level, that UCX or libfabric, that would be very convenient, because that's kind of a smaller part of the problem that needs to be solved on an HPC system. But the disadvantage is that there are many more such small libraries, because there's some for InfiniBand and then C* and shared memory and sending memory to GPUs, and from GPUs different, I mean, at the same time over InfiniBand to another GPU and so on. And then you have many, many small libraries that have an API. And the advantage of MPI is that it's one standard that handles everything for all its deficiencies. So a discussion that we just had here, these are all very valid points, and I tried many of these things. And if I failed, that might have been my mistake. But it is, I think, one of the reasons why people didn't go the route of something like MPItrampoline before, because it seems so tantalizingly close to solve it the proper way, instead of adding another wrapper layer somewhere. But on the other hand, I tried the other things, I failed, and MPItrampoline is now something that I know can be made to work. And I'm really happy here. And of course, something that works on a technical level is only a small part of the problem. What you really need is community buy-in, and actually make it something that is widely used and convince others. And yeah, well, actually, thank you for hosting the talk here. That's, I guess, is the first step in that direction. So I was going to describe the MPI ABI and how that works, how that relates to actual MPI or the bit of a technical level. So the compile time constants that I mentioned, there are just 10 or so. Most other things are actually load time constants. And load time constants is a technical term taken from the MPI standard, but you might not have come across it before. That's essentially, I mean, if you look at the C standard and how linking works on a Unix environment, this is exactly where it comes from. These are essentially global variables. Maybe they have a const qualifier that makes it somewhat more difficult to change them at runtime. And these essentially global variables that are initialized at program startup time. One of these is called MPI world, as the communicator that contains all the processes, allows everybody to talk to each other. MPI also defines certain types. Most importantly, opaque handles such as MPI the communicator. It's a big data structure internally. The user only ever sees a handle, and MPI standard says technically, well, it can be any type, but it also says you must be able to compare them for equality. It's not possible for structs, so it can be any type, but it must be one of the built-in types in the C language. And that leaves essentially just integers and pointers that you could use, and pointers are also very similar to integers. And that in the end just leaves the MPI implementation the choice to use a 32-bit integer, or do you use what is now a 64-bit pointer. And of course, half the MPI implementation do one thing, half do the other thing. And for convenience in the ABI, I thought let's just use a 64-bit type, because if the MPI generates a handle that's 32 bits, it's very easy to convert that to a 64-bit integer, fill in the zeros and pass it to the application. And then this is a very efficient way of converting handles. You take essentially one machine instruction to 0x the value. And constants that the MPI library has, they are exported with the same value. So when the MPItrampoline starts up, it queries MPI wrapper about all the constants. I don't know, there are 100 or 200 constants, mostly various error codes. And it just keeps a list of them, initializes the global variables here after type conversion. And then the actual application uses the same constants as the underlying MPI library, except for 32 64-bit conversions. So that's also a very efficient way of doing things. There are, of course, functions and callback functions, and all the actual MPI functions, well, they're wrapped by MPI wrapper to do the type conversions, and then MPItrampoline just gets pointers to that functions and calls them. So one cost of the interface is an additional function call to a function pointer. I believe that's very fast these days because C++ and virtual functions made sure that all the compilers and CPUs make this efficient. So the division of work essentially means MPItrampoline at runtime queries the MPI implementation for various information that it then presents to the application. And MPI wrapper translates between the ABI and the data types that the actual MPI implementation uses. And I believe the wrapper interface for MPI uses a different approach here. They don't have the wrapper, so I believe the wrapper interface for MPI needs to do the translation. They explicitly specify which MPI implementations they support. So I guess they have hard-coded support how things should be translated. And it also seems to me as if the wrapper interface for MPI looks to the outside like an OpenMPI. So they must be translating certain constants. Maybe via the lookup table at runtime. At startup, MPItrampoline needs to decide which wrapper interface to load, and there are several mechanisms available. The usual thing, there's an environment variable. If that's not that, you can set a global variable. That's sometimes easier to set. Sometimes it's difficult to set an environment variable. If you don't want to do that, you can also hard code or default path into MPItrampoline when you build it. As only useful in very special circumstances. And otherwise, it still works. You just can't call MPI. So if you have an application that maybe wants to use MPI and maybe not, and you link against MPItrampoline and you don't actually set the environment variable, then everything is still fine. You just run without MPI. That's very important, for example, in configure scripts, where certain things want to be run and there's no MPI implementation available. That still works just fine. And now this is where more than half of the work went in. This is the bit of Unix that looks very simple from the outside and very elegant, and there's so much pain and suffering, I'm telling you. So the difference between a shared library that you all know and a plugin is that the plugin needs to be loaded explicitly manually. There's a function for that called DLOpen. You load a shared library, and then all the symbols of the shared library of the plugin, are made available in your namespace. And of course, the problem is we have two functions called MPI in it, one in MPItrampoline and one in the actual MPI library, and they are incompatible. Binary incompatible, they use different types, so if you mix them up, of course, immediate segfault. So we need to fix that. So when MPItrampoline loads the wrapper, then DLOpen has a thing called namespaces, very elegant. You can put the whole thing here into its own namespace, and then essentially the symbol resolution doesn't clash at all. But of course, it's still the same address space. You can still have pointers and so on, and that works just fine. It's the ideal solution for plugins. And the only problem with it is that it does not work in real world. And I was very disappointed to learn that. So this MPI library isn't just one shared library, it's probably 3 or 5, and there are probably more shared libraries that it's load for some reason. MPI implementation like to spread the code on many different shared libraries that are loaded. And every shared library, of course, needs to declare its dependencies. And if it doesn't declare dependencies, then it wants to call a function. For example, if a library depends on pthreads and it doesn't declare that it depends on pthreads, then the library would be loaded, but the pthreads library would not be loaded, and you'd get an error at runtime. Except, of course, if the library is in an application and the application has, for some reason, already pthreads loaded, then you'd never notice that. And this is what happens here. Some of the MPI implementation don't declare their dependencies. Weird libraries, libm, librt, and so on, small things that are usually always loaded. And usually you don't notice that the library is installed incorrectly. But if you have them in their own namespace, there's nothing in here that would say load librt. And if they call librt, that's an undefined symbol error and it crashes. And if you get your MPI library from Ubuntu and Red Hat, then it all works fine. But on an HPC system, MPI libraries are, and I'm sure they're HPC administrators here on the call, but they are often installed in a rather, let's call it, weird way. And I don't mean that in a bad way. I mean, you need to use modules or something like that that make it difficult how things need to be installed and then what is loaded, how dependencies are resolved, and other things, various compiler versions, how it needs to find the runtime system of the compiler. And in practice, I could not find a single system where this namespace, this DLMopen was working on an HPC system. So you can't do that. The other thing, of course, is DLMopen. It's nice. It's a GNU libc extension, so it doesn't work on BSD. It doesn't work on macOS either. So you need to use a different thing. And the other thing you can use is symbol interposition. That's part of shared libraries. If you load two shared libraries that provide the same symbol, for example, MPI init, then all the applications would use the first symbol that is loaded and not the second. And you can fix that using something, and now is the really complicated part of the talk, using either deep bind or two-level namespaces. And that means we have an MPI init here and here. If the application uses MPI init, it uses this one here. If you use these two libraries here, reloading them via deep bind, then if MPI wrapper looks for an MPI init, it wouldn't start looking here at the application, find that MPI init. It would first look within itself and its dependencies. And then if it doesn't find it, then it would continue to look here and the other ones. So MPI wrapper finds the MPI init here. And if the MPI library itself calls other routines in itself, it would also start looking here and then would look the symbols in itself. So this deep bind is a mechanism that makes it work in this case, even if MPI libraries are not completely correctly installed and then dependencies are not there. So if this wants to call a pthread function and the dependency on pthread is not declared, it would then, if it's not found here, wrap around here and then probably found it because some other bit of the application loaded it. And macOS has the same thing. They call it two-level namespaces, and there are certain incompatibilities, but in the end, it works in a similar way. And I was going to say much more, but I realized this is really going off the deep end. So let me stop that. This is probably the slide that you've been waiting for. What about efficiency? MPItrampoline introduces obviously some overhead because there's some going forward and back and some late translation. And they're really intended to present some benchmark results here. Unfortunately, I was busy with some other project around GPU computing, so I don't have any benchmark results, but I have good arguments why it shouldn't be expensive, and you might or might not want to believe me. So the interface layer is quite efficient. MPI handles over 64 bits. The actual MPI implementation might use 32 bits. The conversion from 32 to 64-bit is at most one machine instruction, not expensive. If you have an array of MPI handles, then you, of course, need to kind of compact the array. That's only half the size before. So you need to touch each of the element of that array. But that also doesn't create an undue overhead. So let's talk about MPI wait. If you're familiar with MPI, where you might want for 100 communication requests at the same time. So then, of course, you have to convert all the 100 requests from handles from 64 to 32-bit. But the MPI implementation would also have to look at all of these MPI handles. So that this order n overhead is kind of shadowed by an order n work that needs to be done. The MPI status data structure has 3 extra fields that could be optimized, but not doing that. I don't think that's very expensive. And callback function, when MPI calls in the user code, they also need to be wrapped to fix the handles, of course. All the MPI constants have the same values. That's good. MPI functions, they're called via function pointers that introduces another layer of indirections. But apart from that, nothing expensive happens inside MPItrampoline or MPI wrapper. There's no big data chunks that are copied. Everything is just pointers to buffers that are already passed around. And finally, the current state of things. So the bindings for C and Fortran 77 are complete, except for some of the callbacks. The Fortran 90 bindings are not yet available. I tried it with a few libraries, RDS2, Amrex, Boost, FFTW, HD5PETSI, and so on, and it compiles for all of them. I have no reason to assume why it didn't work correctly. I tested some of them, RDS2, Amrex, FFTW, and so on, in the context of the Einstein toolkit. It works. Boost has a star here because it turns out Boost.MPI used to violate the MPI standard a tiny bit. So did PETSI, by the way. So I sent them a 10-line patch, also to PETSI. And while the PETSI maintainers incorporated that within kind of 3 days, I haven't heard anything from Boost.MPI. For all I know, that library has been unmaintained for at least half a year. So there would be a compile time error, and it's, I argue, their fault because they violate the MPI standard. The OpenMPI test suite passes, except for some things with initializing something. I need to make a small kind of relevant change to the source code to initialize things correctly. And I'm using MPItrampoline in production, built via spec via the Einstein toolkit, working on Julia. And the main point of my talk is let's drag HPC package management, kicking and screaming, into the century of the fruit bat. Let's make sure you can have binary package management on HPC system. And I don't care whether it's MPItrampoline or wrapper interface for MPI or libFFI or something, but I really think you want binary package management. And I'm sorry that you called your thing EasyBuild. If this works out, you might have to rename it to Easy Download or similarly. That is my presentation. Thank you for your interest. And if you have questions, now is a good time to ask.
Right, thank you very much, Erik. Very good talk. Regarding the benchmarks, this is of course something that's important, I would say, certainly in an HPC context. Do you have specific benchmarks in mind, or you're looking at mainly applications, or any micro benchmarks, or?
I was looking for micro benchmarks. Someone pointed me to micro benchmarks for, I don't recall, it was either MPItch or OpenMPI, and I was going to run these, and that should be straightforward. Yeah. And of course, you would want to run them on an HPC system with InfiniBand.
I think the OZU micro benchmarks, those are probably the very popular in the HPC community, and they're actually part of the MPItch project. So one of the MPI implementations.
Oh man, I'm so sorry. I mentioned MPItch and OpenMPI. I definitely should have put MPItch there. I'm sorry to the MPItch developers. I've used it in the past. It's a good library. It's just an oversight of mine.
And that benchmark suite is quite good. Actually, it allows you to test all kinds of things, scatter, all to all. It gives you a nice overview of the latency and the bandwidth and all these things. So that would be a very good starting point, I would say, to check if there's any overhead by MPItrampoline.
And
okay, let's see if there's.
I forgot to mention something else. I called it MPItrampoline because there is a Julia package called Blast Trampoline or libblast trampoline, and that was the thing that finally gave me the revelation that we need the same thing for MPI, hence also the name. Of course, the implementation is very different because MPI carries the global state, so it needs to be same thing beginning to end, whereas libblast, you can switch at runtime several times over from OpenBlast to MKL and back, or could probably even use both at the same time if you handle namespaces. But apart from that, that was the original motivation, was the trigger. Thanks, Bart. Sorry, this is FlexiBlast. Yeah. The thing was called Blast Trampoline, so it's probably a different project.
Yeah, so FlexiBlast is indeed another one that is kind of similar to the Blast Trampoline that Julia uses. And they were also looking at each other for inspiration, I would say. So they're very, very similar to the wrapper MPI library you had and your MPItrampoline. It's a similar situation. There's a question by Mikhail on how this would all work with GPU Direct and RDMA. So I'm not sure if you're familiar with that.
I'm familiar with RDMA, not with GPU Direct.
Yeah, so I would guess when you in a multi-GPU context, how would this also work if you have an MPI program that accesses multiple GPUs? Would that also work?
This package wraps the MPI standard, currently 3.1. I guess 4.1 is currently out. It could easily be extended. So RDMA, there is an MPI specification for that. If you want to use that, get put and so on, you could. If you want to use another library that also provides RDMA or GPU access, then that's not MPI, then you would need to wrap that library. I don't understand the details of the question.
Yeah, maybe Alan has something to add on this.
Well, no, I had more of a question. I suspect that maybe you don't need to know about that, because I suspect that that's something that's happening inside the MPI implementation itself. And that's usually the way something like that would work. So it will handle transferring things between doing the RDMA stuff and the GPUs, but I'm not sure. But I imagine that that's inside the MPI implementation layer. I don't think you make specific calls to a GPU enabled, but I'm not sure actually. No.
What Mikhail says is that you need to know at compile time whether you're going to be passing CUDA arrays or not. So what kind of buffer do you need to use? Do you need to use a GPU buffer or a RAM buffer? And that's apparently something you need to know at build time. So that would be difficult, I guess.
Okay, so MPItrampoline only sees buffers as a void pointer. That's the only thing it ever sees. And that would today essentially be a 64-bit 64 bits, 64-bit integer, and it passes this through to the MPI implementation. So if the underlying MPI implementation knows about GPUs and handles that correctly, then it's the question of how the application and MPI implementation talk to each other about whether a particular buffer supports GPU or not. And I guess, since it's about allocating large amounts of memory, it makes sense to have if statements or if def in the application and to see whether it's on the GPU or not. I haven't thought about it too closely, but you can definitely compile with support for CUDA and then run without using CUDA at the end. You probably have to ship a large part of the CUDA runtime as well to the HPC system, but that's all possible as well. So I think it should work. Not exactly sure whether that's true.
Yeah, it seems like Mikhail agrees with you based on how you explain it, that it might work, but it's maybe something to look into as well.
I just have another question just about, so you mentioned the standard that you currently have, and is it a lot of effort to support a new standard? So, because I know that for the wrapper interface for MPI, there was some time, they lagged a little bit to the standard, right? So they were a bit behind. I was just curious how much effort is involved.
It's not a lot of effort. The thing that's not yet there is being able to kind of choose which standard is supported and what not. And I was afraid that many MPI implementations don't support 4, so if MPI wrapper wouldn't build because it doesn't have any kind of switching mechanism where you kind of choose at build time what version of the standard to support. That's kind of straightforward to add. But apart from that, it uses Python for automated code generation. So each MPI function requires a few lines of Python describing the name of the function and the argument types. And then it creates the wrapper functions and everything MPItrampoline. You need to repeat that for the Fortran 77 interfaces. And some functions require special handling. For example, MPI wait all needs to be implemented manually because it has an array of handles and that needs to be translated manually. So I think it should be a one-day effort to make it work, plus, of course, testing and so on.
Okay, thanks.
Do you have a particular feature in mind that is in MPI4? Maybe I'm missing something. Maybe there's something new that would break my assumptions.
No, I don't. The only reason I ask is somebody raised it on the wrapper interface for MPI on their. It was an issue in one of their things, and then I was curious, like, what would be the blocker? What would slow you down from supporting a newer MPI? I think they were on quite an old one. I don't remember the details, unfortunately.
Okay. Yes, it is a bit sad from me. This is my mistake that there hasn't been a communication between MPI wrapper interface for MPI and MPItrampoline as a project. And the MPItrampoline is the newer one. It's kind of the ball's in our court to talk to them and see what happens there. Because I think it's usually not good in open source if there are two parallel projects doing the same thing. On the other hand, it kind of indicates that the time is ripe for that idea and it should really happen. And I don't care who wins. I want binary packages on HPC systems. I think I mentioned that before.
I think some healthy competition between libraries or projects that largely do the same thing is not actually a bad thing. I mean, look at EasyBuild and Spec. They're both quite popular. They're both used by big communities and supported well. And there's a lot of exchange of ideas there as well. So in some direction, we're implementing features that Spec has, and maybe Spec has done the same thing based on ideas that EasyBuild has. So yeah, I would say as long as the competition is healthy and people are talking to each other, it could be a good thing.
I looked at EasyBuild, of course, before the talk when I started implementing package description for MPItrampoline. And there should be another one for MPI wrapper. But I didn't finish it. We got distracted by other things. And then I remembered that last weekend, and of course, I couldn't finish it. But that's definitely something I need to do. Now, after advertising it, it should be really, really easy for all of you to actually install it and use it.
Yeah, that would be nice if you could share that. Yeah.
Are there some questions in the chat that we skipped? So
well, we've already raised them. I think there was some discussion going on in the Zoom chat rather than any specific questions. The ones that were raised, I think we already covered. And I do have another question myself. So you mentioned this is, let's say, relatively early stages. You think it's ready for production, but it hasn't been tested enough yet. And it's maybe missing some parts like the Fortran 90 part as well.
Yes, I think few packages use them. If you look at Petsy and so on, they all use just the Fortran 77 interface.
Okay.
So if that comes up, if it's important for a project, then I'd be happy to add the respective things, of course.
Yeah. So I was just wondering, what are the next big steps that you see for MPItrampoline? Is it indeed getting better adoption? Is it getting people to try it and see if it works for them, or they run into any trouble, or maybe too much overhead to be useful?
So I think the next big step is to actually use it for the Julia package manager. And there we are producing binaries currently based on MPItch. And I think in the future there should be MPItrampoline with an automatic MPItch as a backend. And the big problem that we're facing, well, apart from winter break that slows everything down for a month, is it needs to be really seamless transition. So if you make a change to all the external packages for Julia, this would be like changing a fundamental package in Anaconda for Python. And I'm more nervous about breaking something during the transition than the actual features of MPItrampoline. But this is something that really interests me, and this is the main driving point for me for the project, to make it more easily possible to use Julia on HPC systems without having to install the whole software dependency tree from scratch.
There's another questions popping up in the chat by Axel. How do you integrate MPItrampoline in package managers? For example, in SPAC as a virtual provider for MPI or something else?
Yes, so I have a SPAC package. It is part of SPAC. It's just an MPI provider. It claims to support MPI 3.1, and that's it. So it's just a regular package. It's written in C. It's a really easy thing. Well, C and Fortran bits for the interfaces, and to use it and build against it. And the only thing is at runtime, unless you set the environment variable and point it to an MPI web actual MPI library, there's not going to be any MPI. And yes, go on.
Yeah, another question related to Julia is MPItrampoline currently supported by MPI.jl? How does the situation look with MPI cluster managers.jl?
Okay, so MPI.jl was a big event where it actually moved to the main branch of MPI.jl. That means if you get the development version, yes, it is supported, but it's not the default yet. And also it's not the released version, so the community hasn't seen it yet. And the idea there is that the people who are more interested in MPI, I want to invite them to try it out and break it and build their own packages against MPItrampoline and make it work that way. And then at some point, since it's not the default, I don't know, in January or so, we can release a new version of MPI.jl, still without MPItrampoline being the default. Let's just be really afraid of breaking something, because if the first impression that people have of MPItrampoline is that the whole Julia ecosystem of MPI packages breaks, that could create a bit of, yeah, no, I don't want that to happen.
And then on MPI cluster manager, so I'm not sure what that is, but.
So Julia has a rather nice way of adding additional processes to it. You said just an add process, and it starts a new process that runs on the local machine. And there's also something built in that just uses SSH on a remote system to add new processes. And it's very easy to get the distributed Julia system like that. And the MPI, and that thing is called a cluster manager. And there's an MPI cluster manager that provides the same functionality, but using MPI instead of SSH to start something. And there are several modes. There are modes where you have one Julia shell as a front end that attacks a whole bunch of MPI processes. Or there's another mode where everything runs on a cluster, where all the processes are MPI processes, and the Julia shell just runs on MPI process 0, the root process. And because the cluster manager has been designed from scratch, you having SSH in mind, it doesn't really fit the MPI model of how processes start or stop. And that is a bit of a clunky piece of software. And apart from that, I don't think MPItrampoline changes anything. It's just another MPI implementation.
Okay, yeah, I think that question was answered. There's another question that was raised, which is sparking a bit of discussion, but let me raise it to you as well. What about different lengths of doubles by different compilers? So apparently, the Microsoft compiler makes long doubles the same as doubles. Intel makes them really longer. So between long double and double, is that a problem for an MPItrampoline or?
Oh, wow, yes, it would be. I completely did not think about that. So the MPI standard has support for long double if the respective compiler supports it. It's really difficult to find out whether, you can check whether the compiler supports it. There are probably feature macros, but I don't think there's any official way to find out whether MPI supports it, because MPI doesn't specify whether there are respective hash defines or not. And I had lots of trouble with long double. So the respective part is disabled. I forgot about that, honestly. Otherwise, I would have mentioned that in the shortcomings. And so that the outside MPItrampoline looks like an MPI implementation that does not support long double. I think that's supported by the standard. And so you don't have to do any of the translations. But in the end, if the size of long double changes, then your whole kind of CPU architecture changes. So you need to know that when you create a binary for an application. And from that point of view, I think MPItrampoline just needs to do the same thing. So that kind of architecture needs to match between MPItrampoline and MPI wrapper. Otherwise, they can't talk to each other. It's the same as the size of an int or the size of a pointer, whether you run on Intel or ARM architecture. So these architecture boundaries cannot be bridged here. And they're actually, that's okay. So there's some architectural incompatibilities created by lib standard C++ versions or libg Fortran versions. And the MPI ABI is independent of that because it's really just based on C, the C ABI, PS ABI. But the size of long double, that needs to match.
So this is currently a problem in MPItrampoline, but it's fixable, or?
No, MPItrampoline doesn't support it. And if it was supported, you probably need then runtime checks whether long double is supported or not. Then it would work out of the box.
Okay.
Because if you have part of your application that thinks a long double is 8 and another part thinks it's 16 bytes, that's really different architectures. It's like different CPU architectures. There's no way to mend that automatically. It's like when you have 64 and 32-bit Intel CPUs. They also have different ideas of work. You can't have function calls across that, and it's same with that.
Currently, there was a comment on the Fortran 90 interface as well. CP2K is one of the applications that does use Fortran 90 MPI interface.
Oh, CP2K, what is that? Is that an
That's
application?
quantum chemistry, yeah.
Okay. I guess I'm looking forward to receiving their feature request.
yeah. And actually, I think one of the CP2K developers was attending the talk through YouTube as well. So you may hear from.
Okay.
Okay. Maybe last call for questions. If anyone has another question, please raise them now or raise your hand here in Zoom.
I did not follow the discussions on the Zoom chat, and the messages will be lost afterwards. So if you want to raise one of these questions, now is a good time, or of course, email later on works as well.
Yeah, we can probably save the chat if you want to catch up on that.
Okay. Oh, I just see the last question. Where's the best place to ask additional questions about? Okay, MPI.jl. Yes, there's a Julia discourse. There's a Julia. Okay, I don't know which of the discourse things, but Julia, I should recommend here. So I'd just say open a GitHub issue on MPI.jl and ask questions there. It's a low volume thing, so anything goes in MPI.jl issues.
Okay.
Oh, and if it's just the general questions for help with Julia, I would follow the advice on the Julia language page, which probably points to some Slack channel or Discourse channel for asking for help. That should also work.
And I guess for MPItrampoline specifically, it's mostly through the GitHub repository currently.
Yes, or if you find me on some elsewhere, you can also ask questions there. But GitHub is always good. It says issue, but I also like it for discussions and questions.
Okay. Yeah, I think that's it. We've had quite a lot of questions, very good questions as well. So thank you again, Erik, for the very good tech talk.
You're welcome. Thanks for having me.
Hopefully we can get some people to play around with MPItrampoline and see how it works for them.
Yes, or the wrapper interface, anything, please, just binary packages.
Okay, thanks a lot.
Bye-bye.